As a disclaimer, I have a focus, a bias on brain mapping. Not every machine learning for brain imaging falls in this description. So it's important to think about our applications. And so in medical applications, I mean, we think we're looking at brains and some might have, some disease, some problem, something we want to look at. And it seems like it's a very well-posed problem for predictive models, right? So the different problems we can solve, and it's useful to understand the different problems we can solve. The first one is diagnosis. So can we, can we predict the nature of a disease condition? Another very important one is prognosis. Can we predict the evolution? And this might be useful because it will enable the doctor to choose different therapies. Another important one is early biomarkers. So the idea here is that we will detect before standard symptoms. And so this could be useful for population screening, and maybe the best example is breast cancer. So cancer in general, in particular breast cancer, if it's detected early, is good chances of a good outcome. If it's detected too late, well, not a good thing. And another thing that we might address is to develop quantitative biomarkers. So the idea is that this is typically the case in a disease that are ill-defined, like neuropsychiatric diseases like autism or even Alzheimer, and neurological disease. So the good thing about a quantitative biomarker is that it's based on the biology and not on the intuition of the physician. And this can be useful for drug development. You're trying to develop a drug for Alzheimer's. Is the drug working or not? Should you wait 10 years for people to die or survive to know whether your drug is working or not? I'm stressing these because it's really important when you do machine learning to think about how it's going to be applied, because it means that the kind of errors and the kind of data you need to work with are going to be different. So it's also really important to realize that we're not, in the short term, going to fully replace the physician. The physician has access to the patient history, so okay, we can try to include the patient health record, but that's an endeavor that goes beyond medical imaging. The physician will decide what therapeutic strategy he will use, because there are logistical constraints, because maybe the patient or the family has a different point of view on this. So the reason I'm stressing this is that apart for very specific problems such as detection of a lesion, detection of a specific aspect in an image, we do not want black box models. We want to be able to explain them, we want to be able to interpret them, because they're going to be used as a tool by the physician to support his decision, and they won't replace the physician. So the problems, the underlying problems are things like segmentation, denoising, as much as prediction. This is what I call the why question. So one thing I'm also interested in is can we use machine learning on brain imaging to understand better brain function? And it's the whole realm of cognitive neuroimaging. So the idea being that you want to link neural activity to thoughts. This is somewhat outside medical applications, even though if we understood this link, we would probably understand better neuropsychiatric disorders. But right now, the realm of the study is mostly on healthy patients. And so the way you can pitch this as a machine learning problem is to say, on the one hand, I have descriptions of measurements of brain activity, and on the other hand, well, on the one hand, I have measurements of brain activity, and on the other hand, I have descriptions of behavior. And then you can try to predict one way, so go from descriptions of behavior to predicting brain activity, or predict the other way, which is to go from activity to descriptions of behavior. Now, if you want to stay in the realm of medical imaging, you just replace descriptions of behavior by descriptions of pathology or clinical situation, and this is the same formal problem, right? And it's important to realize that there are two different questions, and both are interesting. Okay? And by the way, this first question is the typical way of doing brain mapping. So masked univariate standard analysis is really a statistical model that tries to explain brain activity, brain measurements from descriptions of behavior. And an additional thing that we could do is that we could run unsupervised learning on massive amount of brain imaging data, and this might be useful to find some form of informed data reduction, such as brain parcellations. So in fMRI, this is typically done in resting state. Okay, so the reason I'm explaining this is because NiLearn sits in all those different use cases and tries to make them easy. So typically, the most common problem is a problem that people often want to work on is decoding. The idea being that you're going to try to predict from brain data some stimuli or some pathology. The nice thing in this, if you use a linear model, is that the coefficients of the linear model are brain maps. So they're highly interpretable for a good reason. Now, another setting in unsupervised learning is resting state fMRI. And the core intuition of why this is important is simply because data without labels is cheaper and universal. You can accumulate data without labels. The problem is it often comes without salient features. This is an image of resting state brain activity, so nothing really sticks out. And if I played a movie, it would just go flash, 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 and you wouldn't be able to see anything. So the way we tackle this is we decompose this brain activity in different functional regions, and then we learn interactions. And then based on these interactions, this interaction graph, which we call a functional connectome, so connectivity, brain connectivity, then we can look across subjects, across conditions, and detect differences or do a supervised learning task. So this is a pipeline that we've been working a lot on, which is to go from REST fMRI to biomarkers. And the idea is that for neuropsychiatric diseases, this is probably important because it's a way of capturing brain activity, so function, brain function, and neuropsychiatric disorders